All right, the samples that we're studying are in the realm of continuous deformation and penetrative fabrics, where penetrative refers to foliation and lineation, or in this case, two foliations and a lineation that we've introduced. Now, I want to make an aside for a moment and just show you a few samples that express discontinuous deformation or brittle failure. Good examples are these tephras from the off axis of the Rio Grande Rift that have shear faults. Okay, so here's the volcanic rock. You can see in there that the phenocryst and small mineral grains have no preferred alignment. It's very, of course, this is a glass matrix, so there's really not much to see there. But on a side where a brittle surface, or two of them, have broken through, there's strong oxidation, there's fault mirroring, if you can see the glint, and there's very strong streaks that in this case are slicken lines. They're physical grooves in this very discrete surface. All the deformation got localized on that slip plane. Here's another example of a tephra. It has a strike and dip mark on it, and although the surface is not as polished or mirrored as the first one, we can still see the through-going streaks of oxides and the grooves of the lineation. Motion plane for brittle faults has a geometrical similarity that those for gneisses. It's perpendicular to the plane, parallel to the lineation. As an interpreter, we would take a view down of that motion plane to study features to determine whether the strike slip fault moved right or it moved left. One more example of brittle deformation that potentially could offer a twist is fault surfaces that are ornamented with mineralization. These are crystal fiber steps of calcite on a fault that cut the Fort Hays limestone. This is from Canyon City. We can see that the limestone is in perfectly good shape everywhere else. There's no foliation, there's no lineation. All of the deformation was localized on the slip surface. There are crystals, and the crystals grew into a direction of slip. How do we distinguish the difference between these slicken fibers and striae, or lineations that have to do with metamorphic conditions? We take a check and we see that there's not penetrative deformation in the host rock. So this is another example of brittle deformation. We'll go back to continuous deformation now. And the set of samples that I'll conclude with all are rocks that are termed mylonites. This term mylonite has a root. The word origin refers to a verb that has to do with milling or grinding. So we can take this term mylonite to mean milled down rock, as in a grinding, milling down between a grinding wheel for preparing wheat. Put the grain in here, the thing goes around, milling down to reduce the grain size. If it's wheat, so that the material can be used for human consumption, as in baking. If it's mylonite rock, it's grinding and milling down cataclasis that grain size reduces the feldspars. In mylonite rocks, it's accompanied by a different type of deformation in the quartz, very plastic or ductile deformation. So there's mixed fabrics of flow and breaking without losing cohesion of the rock. Quartz flows, biotite, recrystallize, dynamic, it does dynamic recrystallization, as you've learned about. and the feldspar breaks into smaller grains and does dissolution, mass transfer to create this beautiful systematic asymmetry in the feldspar grains that we can define any one as having a sort of an S shape, a sigmoidal shape. These features that make for the beautiful fabric in the rock are called sigmoclasts. Now, why not sigma phenocrysts or sigma porphyroblasts with a B? This term clast refers to the milling down or the grain size reduction. A process term for that is cataclasis. Clasts are the products of cataclasis. Okay, so the myelinite, I have one example in a rock, and I have several examples in slabs. This one's from Antarctica. This one is from the border of Montana and Idaho. This one is from near Revelstoke in the border between Alberta and British Columbia. So this is a question for you all. Where would the motion plane be for this rock? There's a lineation like this. How should I look at this rock if I would like to interpret, in absence of any context around it, where is the hanging wall? Where is the footwall? What is the motion sense across this zone, which is part of a zone about 4.5 kilometers thick, all of which has the same fabrics? How can I interpret this to understand, well, which way were the rocks above the shear zone and below the shear zone moving with respect to each other? So just to pause while you work that out with the sample. And I'll just ask you a rhetorical question. Is the motion plane like this? If so, why? Is the motion plane like this? If so, why? What are the geometrical controls that you're using? Is the motion plane like this? Hopefully you said no to all those things, and you recall that the motion plane is oriented perpendicular to foliation and parallel to lineation. So as far as the viewing direction that holds information of interest, it's this one. In projection planes, we can do whatever we want with. We can move them up and down, project them left and right. What we've done is realize, well, parallel to lineation, perpendicular to foliation, we have a well-placed surface here. If we look into this from the side, we can find features that are interpretable in terms of a kinematic sense, and look for systematic geometries to help us orient the strain axes. We want to use this information about foliation and lineation to determine the X, Y, Z axes of strain. As a field rule of thumb or a hand sample rule of thumb, we can use the foliation to help orient the Z axis. The foliation plane, loosely speaking, we're going to say is perpendicular to Z. The lineation is parallel to X, the intermediate axis Y, is the pole to the XZ plane. Furthermore, I'm sure you've worked it out in your heads. The motion plane is the XZ plane of strain. Okay, and we will assume, and most times this is correct, assume that all change in shape and orientation is expressed in XZ. Okay. Now, a trick with this sample, which is a SC myelinite, is there's more than one foliation. This sample, and I'll put two of them here to be both in view. These have some very strong through-going planes that cross the sample from left to right, and then short intermittent planes that are at an angle to those that cross the whole sample. Okay, which one is which, and which is the one that is perpendicular to the Z-axis of strain? Okay, so I'll just make a sketch as geologists commonly do. And let's focus on this one first because it's quite clear. And just a moment, I'm going to make it brighter. You can